Hello. Today we are talking about Module 4, which is the physical layer. So before any network communication can occur, a physical connection to a local network must be established. This connection could be a wired or wireless, depending on the setup of the network. So as an example, in many corporate offices, employees have desktops or laptop computers that are physically connected via a cable to a shared switch. This type of setup is a wired network. Data would be transferred through a physical cable. With wireless devices, data is transmitted using radio waves. Wireless connectivity is common as individuals and businesses alike discover its advantages. Devices on a wireless network, however, must be connected to a wireless access point or wireless router. And that access point or wireless router has to be physically connected back to the actual backbone of the network. So there is still that physical connection that needs to happen. A network interface card connects the device to the network. Ethernet NICs are used for wired connections, whereas wireless local area network cards, or WLAN NICs, are used for wireless. Some devices may have just one NIC, while others may have multiple NICs, wired and or wireless, as an example. So in today's world, today's network, most devices today come with both already embedded on the motherboard. Now, your physical layer transports bits across the network media. So it is going to accept a frame from the data link layer, which is the layer right above it. It is going to encode it in a series of signals that are transmitted to the local media. So again, those signals are dependent upon what type of network you have in place. This is the last step in that encapsulation process. So the next device in the path to the destination receives the bits and re-encapsulates the frame, then decides what to do with it. So again, we're talking about, and I've spoken about this numerous times in class, the router. As it traverses the network, the router needs to unencapsulate it to find out its information, which is the IP addressing destination. And then if it finds a way to get it toward the destination, it will re-encapsulate it again with data link and trailer information and send it along to the next router en route. If it does not have a path, however, it would drop that piece of information. Now, the destination node physical layer retrieves these individual signals from the media, restores them to their bit representations, and then passes the bits up to the data link layer as a complete frame. The physical layer consists of electronic circuitry, media, and connectors developed by engineers. So the TCP/IP standards are implemented in software and governed by the organization IETF. Therefore, it is appropriate that the standards governing this hardware are defined by the relevant electrical and communications organizations. So your physical layer standards are implemented in hardware and are governed by many different organizations, including the ISO, the EIA-TIA, the ITU-T, ANSI, and IEEE. Now, your physical standards address three functional areas: your physical components. These are the electronic hardware devices, your media, and other connectors that transmit the signals that represent the bits. Hardware components such as your NICs, your interfaces, and your connectors. The cable materials and the cable designs are all specified in standards associated with this physical layer. Encoding or line encoding is a method of converting a stream of data bits into a predefined code. So we're going to talk a little bit about encoding. You are not held to know exactly how encoding works or the different types of encoding processes. I do have a handout in your handouts folder for anyone who is interested in delving a little bit deeper into the different types of encoding. Encoding is the method or pattern used to represent digital information. This is similar to how Morse code encodes a message using a series of dots and dashes. And then the last component is the signaling. Your physical layer must generate the electrical, optical, or wireless signals that represent the ones and zeros to place on the media. The way that the bits are represented is called the signaling method. The physical layer standards must define what type of signal represents a 1 and what type of signal represents a 0. So as an example, if I am talking about a copper wire, my 1 could be represented by 5 volts, my 0 could be represented by 0 volts. If I'm talking about fiber, it would be light for a 1 or no light for a 0. Now this is an example of encoding. Encoding is going to convert the stream of bits into a format recognizable by the next device in the network path. This encoding provides predictable patterns that can be recognized by the next device. So this graphic that you see here is solely for the human network for us to try to interpret and understand what it is your device is understanding. There are different examples of encoding methods. The one that you're looking at here is the Manchester encoding. Shown in the figure here is Manchester. Then you also have the 4B, 5B, and 8B, 10B. And again, see the handout for more interesting information having to do with each. In this example here, within the Manchester, what the Manchester does, as to not overtax one wire over the other, in the middle of a bit time, it will transition its state. So if it starts out as a 0, it is going to transition to a 1. If it starts out as a 1, it's going to transition to a 0. So in this example here, we started out high as a 1, and then we went mid-bit stream, and then we went down to a 0. Now, we go to the 0, and we stay at the 0 until we get into the middle of the next bit stream. The next bit stream, we look to the bit that is here. This bit is 1, so we go high and then to the middle of the next bit stream where you see a 0, and then we go low because it is a 0. Okay, and now because there's two zeros together, it kind of middle of the bit stream here, it goes high, and then it goes down low again to the next 0 here. And then again, next bit stream, it goes high, and vice versa. That is how Manchester encoding works. 4B, 5B takes 4 codes and makes it a 5-code encoding. Likewise with 8B, 10B takes 8 bits and encodes it as a 10-bit series. Now again, graphical representation for us. The signaling method is how the bit values of 1s and 0s are represented on the physical medium. The method of signaling will vary based on the type of medium being used. So again, this signaling has to do with whether we're using copper, fiber, wireless, any type of media for that transmission. So the top one here is light pulses over fiber optic, where I see light pulse identified also in a bit time. And then after that, we have voltage as a digital signal, and that would be the series of 1s and 0s defined as what identifies a 1 and what identifies a 0. The next one is also, these are all voltage signals, so you're all talking about, on the bottom one, different signals here. So AM is amplitude modulation, FM is frequency modulation, and PM is pulse modulation. Again, really all you need to know. And what you're trying to figure out and what you're trying to pay attention to is, again, if I look at the AM graph, I start out at 0, say this is my, actually this is my 0. I would think here is my, maybe not, I'm going to call this one 0. So here, I go above the 0, then I dip down, then I go up, then I go down, then I go up, then I go down. And this is based on amplitude. Which is the height. Next is frequency modulation, same premise. And frequency is how often within that bit time. And lastly, you have pulse modulation. Okay, so again, how often does it pulse? Then over here, oh, these over here, microwave signals over wireless. My bad, this is all wireless. I said it was physical. So these are all wireless over here on the right-hand side. This is your fiber. And down here is your electrical signals over copper wire. So the whole premise I want you to take away from this is identifying what represents a 1 and what represents a 0 based on that series coming from the NIC card. So do not forget, your NIC card places signals of 1s and 0s referred to as that bit stream at the source. It then places it on the medium to go across the network, where at the destination, the process would be reversed. So, it is your NIC doing encoding here, and it is your NIC doing decoding here. Okay, so your NIC is responsible for placing the bits on the medium as well as taking them off of the medium. Now, bandwidth is the capacity at which a medium can carry data. Everyone refers to, oh, my speed is bandwidth. It's actually incorrect. Digital bandwidth measures the amount of data that can flow from one place to another in a given amount of time. How many bits can be transmitted in a second? That is what bandwidth is. What is the capacity that can be transferred in 1 second? Okay? Physical media properties, current technologies, and the laws of physics play a role in determining available bandwidth. Bandwidth is also sometimes thought of as the speed that bits travel. However, again, this is not accurate. Bits are sent at the speed of electricity. The difference is the number of bits that are transmitted per second. So as you see in this chart here, the measurement for bandwidth is bits per second, BPS. So 1 BPS is the fundamental unit of bandwidth. And then the further up we go, and we increment in 3s, kilobits, 10 to the 3, megabits, 10 to the 6, gigabits, 10 to the 9, terabits, 10 to the 12. And that exponent simply means, in layman's terms, or easier to remember representation, is how many zeros after the 1. Now, a few bandwidth terminology you need to be familiar with. Latency is the amount of time, including delays, very important, for data to travel from one given point to another. In an internetwork or a network with multiple segments, throughput cannot be faster than the slowest link in the path from source to destination. Even if all or most of the segments have high bandwidth, it will only take one segment in the path with low throughput to create a bottleneck in the throughput of the entire network. Now, throughput is the measure of the transfer of bits across the medium over a given period of time. Due to a number of factors, throughput usually does not match the specified bandwidth in physical layer implementations. Throughput is usually lower than the bandwidth. There are many factors that influence throughput. The amount of traffic on the wire, I'm using copper as an example here, the type of traffic that is traveling, the latency that is created by the number of network devices encountered between source and destination. Do not forget, every time your information flows through an intermediary device, there is a certain amount of latency that is added on. Okay, so through a switch, through a router, through a repeater, there are seconds, milliseconds of time that device has to look for information in order to send it toward its path. Now, goodput is the actual measurement of usable data, okay, being transferred over a given period of time. So goodput equals throughput minus traffic overhead for establishing sessions, acknowledgements, encapsulation, and all those retransmitting of bits. Now, copper cabling is the most common type of cabling used in networks today. It is inexpensive, easy to install, and has very low resistance to electrical currents. Some limitations, however. Attenuation. Attenuation is defined, or can happen the longer the electrical signals have to travel, the weaker they get. The electrical signal is susceptible to interference from two different sources, which can distort and corrupt the data signals. Electromagnetic interference, EMI, and radio frequency interference can distort and corrupt your data being carried by your copper cables. Potential sources of these include radio waves, electromagnetic devices such as fluorescent lights, electric motors, microwaves, anything of that nature. So attenuation again. If I take, and what we're going to learn is your cables have specified lengths that they can run successfully without incurring attenuation. If I take that cable and I push it past its limitation of how far the run can be, let's say 100 meters. If I take that cable and I push it past its limitation and I do not have an intermediary device in between source and destination, that opens the door for attenuation, loss of signal. Now, crosstalk is a disturbance caused by the electrical or magnetic fields of a signal in one wire to the signal in an adjacent wire. Let us not forget, copper is an inductor, okay? It generates potentials, okay? I could have two different wires with a potential that will really harm one or the other. Now, the way that we mitigate this, strict adherence to cable lengths must be followed in order to mitigate attenuation. Some kinds of copper cable mitigate EMI and RFI by using a metallic shielding and grounding. Some kinds of copper cable mitigate crosstalk by twisting opposing circuit pairs together. Again, I can either potentially be a positive or I could potentially be a negative. If I twist those two together, they will cancel each other out. It's like having a positive 1 added to a negative 1. So different types of copper cabling. We have unshielded twisted pair, shielded twisted pair, and coaxial cable. within the realm of untwisted shielded pair. It is the most common networking media. It is terminated to an RJ45. So not only does Cisco need you to know what type of cable it is, but it also needs you to know, or they also need you to know, what is the terminator, the connector on the end of that cable. It interconnects hosts with intermediary network devices. Key characteristics. Number one, it has that outer jacket that is going to protect the copper wires from physical damage. If you happen to run a wire on the floor, you want to protect the 8 inner wires from damage. So if somebody were to roll over it with their chair, something like that, step on it, you might damage the outer wire, the outer casing, but hopefully you do not damage one of the 8 transmitting wires that are encased inside it. Twisted pairs, again, are going to protect the signal from interference. Color-coded plastic insulation electrically isolates the wires from each other and identifies each pair. Your shielded twisted pair has better noise protection than UDP. It is also more expensive than UDP and is harder to install than UDP. Also, however, terminated with an RJ45 and also interconnects hosts with intermediary network devices. Just looking at the difference between this and the previous slide, you see a lot more things going on here. You see, again, the outer jacket that protects the copper wires from physical damage. Then you see a braided foil, which is going to protect against EMI and RFI. And then again, you see a foil sheared shield for each of those pairs of wires. Also more protection against outside interference. And then lastly, the color-coded plastic insulation, which electrically isolates the wires from each other and identifies each pair. So a lot more protection with the shielded twisted pair. Then you have your coaxial cable. It consists of an outer jacket to prevent minor physical damage, a woven copper braid or metallic foil, which is going to act as the second wire in the circuit, and as a shield for the inner conductor. A layer of flexible plastic insulation, and also a copper conductor. Oh, I said it was a conductor, an inductor earlier. I'm sorry, it's a conductor. Used to transmit the electronic signals. There are 3 types of connectors used with coax, commonly used in the following situation. Wireless installations, such as antennas to wireless devices, or cable internet installations at the customer premise. So it has 3 different types of connectors that you need to be familiar with: the BNC, the N-type, and the F-type. Now, UDP has 4 pairs of color-coded copper twisted together and encased in a flexible plastic sheath. No shielding here is used. That is STP that has that extra shielding. UDP relies on the following properties to limit crosstalk. Again, crosstalk are those 2 wires interacting and creating interference. Each wire in a pair of wires uses opposite polarity. One wire is negative, the other wire is positive. They are twisted together and their magnetic fields will effectively cancel each other out, and outside EMI and RFI. Also, what you want to notice is the variation in the twist per foot in each wire. Each wire is twisted in a different amount, which also helps to prevent crosstalk amongst the wires in the cable. So you can see here, you have a twist here. You have a twist here, here, and here. This one has more. This one is still offset. Okay, then this one is even further away. Okay, so all of this helps with crosstalk, which is interference. Now, standards and connectors. Standards for UTP are established by the TIA-EIA. 568 standardizes elements like cable types, cable lengths, connectors, how you terminate it, how you test it. Now, what you should have seen or will see when we do our cable lab is every wire is stamped by EIA-TIA or TIA-EIA with their particular standards. There is also a handout in your handouts folder that goes into what each one of those cabling stamps mean, just for FYI to you, for anyone who is curious. Cables are placed into categories based on their ability to carry higher bandwidth rates. So electrical standards for copper cabling are established by the IEEE, which rates cable according to its performance. So you start off with what used to be the standard, which is Cat 3, okay, originally used for voice communication over voice lines, but later used for data transmission. Then you go to 5 and 5E, used for data transmission. 5 supports 100 megs, 5E supports 1,000 megs. And this is what you need to know. As a matter of fact, if you look at that handouts folder, there is a chart in there that will tell you how far they can run, what is their capability. That is what you need to know with regard to the different cabling standards. 6 has an added separator between each wire pair, as you can see down here. Okay, so it has this extra sheathing here, this little grayed out area here that also helps prevent interference. Now, while this is very good, it makes category 6 very difficult to deal with as far as wiring it or snaking it through something. It makes it very stiff and very stringent, whereas UTP, regular 3 and 5, is very flexible. It does, however, support speeds up to 10 gigabits. 7 supports 10 as well, and 8 supports 40. So when you look at that handout, in the handouts folder, you're going to see it just continues, speed-wise, just continues and continues to grow. Now, your connectors. You need to be familiar with your connectors. An RJ45 connector, again identified by TIA-EIA 568 standard, describes the wire color codes to pin assignments or pinouts for Ethernet cables. We're going to learn about 3 different cables that you need to be familiar with: a crossover, a straight through, and a console. Now, up here on the right-hand side, when you make your cables, the bottom is a properly terminated cable. You want that cable beyond that little indentation in the RJ45. So it needs to go beyond this little indentation here. You want the wire well up past here, because when you crimp it, this is where it crimps. And you crimp it to make sure that they do not come out of the RJ45. Now, in the picture above, you have all these wires exposed. They can get cut, which equals loss of transmission. Okay? Loss of transmission. So that wire should never, or those wires should never be exposed like that. Next, you have a socket. So when you're thinking about this, we have multiple different ways that you've seen in the lab. You have the patch panel up on the racking system. You have the ports in the wall. So this RJ45 socket is what you're looking at with regard to the ports in the wall. Okay, and on the back of that socket still is that color code On the back of this patch panel, if you were to flip it over, is still a color code that tells you how you're going to terminate. So the order that you put these 8 wires in determines what type of cable it is. So as you see here, straight through and crossover UTP cables, there is also another cable referred to as a rollover cable. This is what I want you to remember as also your console cable. Now, using a crossover or straight-through cable incorrectly between devices may not damage your devices, but connectivity and communication between the devices will not take place. And of course, this is more having to do with older equipment. Okay, when you're using older equipment, you definitely need to use the right cable for the right function. Now, as you see up here, we have 2 different standards from TIA EIA. One is the 568A and one is the 568B. So what you're going to notice from this is how the pairings happen. Okay, now peer 1 is the same between both. Okay, peer 2 is different. In 568A, it is 3 and 5. I'm sorry, 3 and 6. That are going to peer or cross over with 1 and 2. Next, you have peer 3, which is 1 and 2, that are going to cross over with 3 and 6. And then lastly, you have peer 4, so on 568, it is the same on 568B. So these 2 are also the same. Now, your Ethernet straight-through cable has both ends 560A or 568B. Okay, so a straight-through means you are going on one end, and either end has to be both one or the other. But you are pinning 1 through 8 on this side, and 1 through 8 on that side, meaning identical, okay, identical. So on this end, if I'm starting with a white, green here, my other end is also starting with a white, green, and following this succession. Host to network device. So unlike devices, next, we have our Ethernet crossover, and you see this little notation here, okay? We'll talk about that in a moment. In a crossover, one end is 568A, the other end is 568B. So, pins 1 and 2 are crossing over with pins 3 and 6. They are for host to host, switch to switch, router to router, NIC to NIC. NIC to NIC means router to PC. So they connect like devices. And then lastly, you have a rollover cable, again, which is your console cable. It is Cisco proprietary, meaning developed by Cisco. So Cisco has that little light blue cable that usually ships with each piece of equipment that you purchase, or else they used to years ago. I don't know if they still do, but that cable is proprietary to Cisco. You can make your own rollover cable. In order to make your rollover cable, on one end, you're going to pin 1 through 8, and on the other end, you're simply going to flip it over, and you're going to pin 8 through 1. What it is used for: host serial port to router or switch, console port. So used for management of your device. Now, properties of fiber optic, not as common as UTP because of the expense involved. Ideal for some networking scenarios. It transmits data over longer distances at higher bandwidth than any other networking media. It is less susceptible to attenuation and completely immune to EMI and RFI. It is made of flexible, extremely thin strands of very pure glass. It uses either a laser or an LED, a light-emitting diode, to encode bits as pulses of light. The fiber optic cable acts as a waveguide to transmit light between two ends with minimal signal loss. So LED again is a light emitting diode. Okay, a diode is something that happens in electrical terms. It kind of looks like this. And this is the part that would light up. And it has 3 little stands. And this you would plug into a circuit board. That's about all I'm going to teach you about electronics. Although I do love electronics. So if the power is on, your LED would be lit. If the power is off, your LED would not be lit. It is quite simple. So as a matter of fact, when you're looking up at your devices and stuff, all those green or yellow or amber lights that you're seeing, those are your LEDs. Now, there are 2 types of fiber: single mode fiber and multi-mode fiber. Single mode produces a single straight path for light. So this one is the one that is using lasers. And just like we were told ever since we were children, just like you would not look into the sun without sunglasses or some kind of protectant, you do not look at a live fiber optic cable. It is a laser beam. It has a very small core. It has a glass cladding. And then it has a polymer, I can never say this word, polymeric coating. It is good for long distance applications. Usually an aqua color would define a fiber, single mode fiber. With multi-mode, and so as we said, in single mode, it is one straight beam of laser that stays within the channel. So this is a mirrored channel. So what you want is reflection, okay? So this is a mirrored channel. So this is reflection. You want it reflected. Reflection is good, okay? It keeps it within that channel. Now, with multi-mode fiber, They are using those LEDs, and they are using multiple. So what happens here is you have a bigger channel, and you have different LEDs going off. Now, what happens is sometimes you could get disbursement, meaning it goes outside of where it's supposed to be. Okay, so that would be considered a form of attenuation, still a loss of signal. So again, a larger core uses less expensive LEDs. The LEDs will transmit at different angles, and it is up to 10 gigs over 550 meters. So dispersion refers to the spreading out of a light pulse over time. Increased dispersion means increased loss of signal. Excuse me. So this up here is dispersion when you go outside of that channel. I've also heard it referred to as refraction, reflection and refraction. Reflection is good, dispersion is not. So MMF has greater dispersion than SMF because, again, it is dealing with multiple LEDs. The maximum cable distance for MMF is 550 meters. Now, fiber optic is now being used in 4 types of industry. Enterprise networks, which is used for backbone cabling, which is where you'll see most of fiber being utilized. So backbone cabling applications and interconnecting infrastructure devices, like if you had a campus, interbuilding, connecting in between buildings on a campus. Fiber to the home, used to provide always-on broadband services to homes and small businesses. Then you have long-haul networks, used by service providers to connect countries and cities. And then you have submarine cable networks, used to provide reliable, high-speed, high-capacity solutions capable of surviving in harsh undersea environments at up to transatlantic distances. So anyone interested in this very cool topic, if you Google transatlantic cabling, you will find the entire map of how they have cabled under the ocean. Very cool stuff. Our focus in this course is the use of fiber within the enterprise. We will not be making fiber cables. You need to be specially trained in order to work with fiber optics. Your connectors, a straight tip, ST, one of the first connector types used. It locks securely with a twist-on, twist-off bayonet style. Your lucent connector, LC, are smaller version of the SC connector, the subscriber connector. These are sometimes called little or local connectors and are quickly growing in popularity due to their smaller size. Then you have the subscriber connector, SC, referred to as square connector or standard connector, widely adapted in LAN and WAN connectors that use a push-pull mechanism to ensure positive insertion. So you actually hear them click when they go in. And then you have a duplex multimode LC connector, which is similar to an LC simplex, but uses a duplex connector. So one thing you must remember about fiber optics when you're looking at the cable, it will start out, for the most part, it is going to be one single running cable. It looks like a single cable, however, it is actually 2 cables that are together. And it looks like a single cable for most of the run until you get to the end. At the end, each cable would go off to their tip or their connector. That is for transmitting and receiving, because they run at full duplex, which means simultaneous communication. Which is that transmitting and receiving in both directions. Now, for the most part, I mean, and color is always subjective, but basic rule of thumb, a yellow jacket is for single mode fiber cables, and orange or aqua is for multi-mode cable. In these labs, your crossovers are either yellow or orange. In this picture, you see that both types can either be yellow or orange. But in our lab, if you look up at the switch that is connected to the main distribution facility, it certainly is aqua. So again, no set standard. Now, this is a slide that you should print down and keep with you. This is optical fiber, which is primarily used as backbone cabling for high traffic point-to-point connections between data distribution facilities and for the interconnection of buildings and multi-building campuses. So this is a comparison between both. So as you can see, UTP cabling has slower bandwidth, much more susceptibility to EMI and RFI and to electrical hazards. However, it has the lowest cost with regard to media, connectors, installation, and safety. Fiber optic, you're going to get longer distances with higher speeds. You're going to be totally immune to RFI and EMI, and it is going to be, unfortunately, the highest cost factor with regard to media and connectors, installation, and safety precautions. So again, up until recently, you only used fiber in your backbone cabling, which is the main structure of your network. Just like your backbone, your spine is your backbone. It is where your central information is all stored and where it goes out from. Same thing with your data backbone. So you definitely want your fiber there. Now, your wireless media carries electromagnetic signals representing binary digits using radio or microwave frequencies. This provides the greatest mobility option. Wireless connection numbers continue to increase, mainly based on ease of implementation. You're not bound to a geographic location, things of that nature. Some limitations, however, the coverage area. Effective coverage areas can be significantly impacted by the physical characteristics of the deployment location. Take CCRI here on this campus. It is a cinder block building. You could come into the structure, have wireless, walk down the hall, lose it, walk a little further, get it, walk in the alcove, lose it. It's better today than when it first started out, but these are your limitations. So what happens is when you do what's called a survey, a wireless survey for an organization, you have to think about overlapping your channels. So if I overlap my channels, okay, this is where your overlapping happens between your channels in this little space. Okay, so overlapping is here. So you would assume, hopefully, that if somebody were now walking down the hall, they might start here, then they're going to use this overlapping to continue going, and then they're on to the next. Pretty much that's how it works, so that you're not losing signal as you walk around the building or wherever you are where wireless is being implemented. Wireless is susceptible to interference and can be disrupted by many common devices. Security, wireless communication coverage requires no access to a physical strand of media, so anyone can gain access to the transmission. However, do understand that however you're gaining your wireless connection, okay, however you're gaining your wireless connection, either through an access point or a wireless router, those need to be physically connected to the backbone. It is referred to as shared medium. WLANs operate in half duplex. So if you remember what half duplex is, it means one device transmitting at a time. I apologize, I didn't realize it was right here. And so again, it is also unidirectional, meaning that one device sends information. Everybody else has to wait until that information is completely received before the response, which is also one direction back, and all the other devices have to wait for that to happen. So it is not optimal. Many users accessing the WLAN simultaneously will result in reduced bandwidth for each user. Now, IEEE and the telecommunications industry standards for wireless data communications cover both the data link and the physical layers in each of these standards. So, physical layers specifications dictate data to radio signal encoding methods, frequency and power of transmission, signal reception and decoding requirements, and antenna design and construction. Do not think that the only antenna in wireless is the one that you see coming off of your wireless router or your wireless NIC card. Okay? You have multiple different antenna, and that is what a wireless company would come in to do when they do their site survey. Not only where you need that overlapping that I described, but what type of antenna do you need for the best signal for your organization. Now, standards that you need to be familiar with. Wireless in totality is defined in 802.11 for Wi-Fi. It is a wireless LAN technology, which stands for wireless fidelity. It is a wireless networking technology that enables devices to connect seamlessly to a network via radio frequencies. You need to know that 802.11 within that wireless realm identifies Bluetooth, which is a wireless personal area network, or a YPN. It is a wireless technology that allows devices to communicate with each other without cables or wires. WiMAX is defined in IEEE 802.16. It is a wireless technology that provides high-speed internet access over longer distances. It uses a point-to-multipoint topology to provide broadband wireless access. It is an option to DSL and to cable. And then lastly, Zigbee is IEEE 802.15.4, and it is a wireless technology that allows low-power devices to communicate with each other without using a lot of power, and primarily used for the industrial and the Internet of Things applications. In general, a WLAN or wireless LAN requires the following devices: a wireless access point, which is going to concentrate wireless signals from users and connect to the existing copper-based network infrastructure, and wireless NIC adapters, which provide wireless communication capability to network hosts. There are a number of different WLAN standards. Pay attention to the ones I outlined in the previous slide. When you are, however, purchasing your WLAN equipment, you need to ensure compatibility and interoperability. A lot of the standards are not backward compatible, so you have to look into that feature before you purchase anything to either enhance what you already have, replace, whatever. Okay, compatibility is a big issue with wireless. Network administrators must develop and apply stringent security policies and processes to protect WLANs from unauthorized access and damage. It is a terrific area for security threats.